Hey everybody, I'm Garrett O'Hara and I'm going to be presenting on the topic of graph theory. And graph theory, I think so far is my favorite topic within mathematics. I was introduced to it in my data structures class with a really awesome professor, learned a little bit more about it in discrete math, and then I'm also learning some additional really cool algorithms that you can do on this topic in my algorithms class. We'll keep it simple today, and hopefully you're able to learn something about graph theory. So, when you think of the term graph, a lot of people are going to think of something like this. This is a Cartesian plane. This is a two-dimensional Cartesian plane, and we have axes here, x and y. There's also three dimensionals, which have x, y, and z. It's used a lot in Calculus 3. And this allows us to put points in space with meaning. And we have the point D, which is a certain distance away from the x-axis and the y-axis. B is at the origin, C obviously. And we can represent these points in a few different ways. Right now, this is kind of set up with ordered pairs or Cartesian coordinates. We could also do polar coordinates, which have a certain distance and rotation in respect to the x-axis. But this is not the kind of graph that we're going to look at today. It's something a little differently. So you might be asking, then what is graph theory? And at a broad topic, graph theory is a subtopic of discrete math, which is the study of finite numbers. A lot more people are more familiar with calculus, which deals with continuous numbers. That doesn't really make a whole lot of sense at first, but if you think about calculus, something you do a lot is integrals. And what an integral does is that it measures the area underneath a curve. A lot of times that curve doesn't resolve to a whole number, something like the number 2, 3, or something. And what the integral allows us to do is give a really accurate approximation of the area underneath that. Same thing with limits. Sometimes you don't really approach a finite number. Where in discrete math, we don't really do that. There's no limits or anything. Everything is with whole numbers. This quote right here, I grabbed off a website, and it describes graph theory. But essentially, graph theory is just the study of things that are connected or not connected in really good detail, as you'll see. A little bit about the history of graph theory. Unsurprisingly, the foundation of graph theory was founded by Euler. He's responsible for so many other things as well. Could pretty much do a whole class just on Euler's findings in mathematics. Just to name a few that are pretty profound. The natural number E, I'm sure a lot of people have seen this. And Euler's method helps you solve ordinary differential equations a lot more. He's a pretty smart guy. And how his finding in graph theory came to fruition is an interesting story. And someone proposed a question to him about this town in, I believe, Germany called Konigsberg. And they asked him, hey, Euler, can I traverse across all land masses in this picture and cross every bridge only once? At first, he didn't really like the question, but being a thinking man, he kept thinking about it. And he noticed that there really wasn't anything in the current math space that could accurately describe or prove this question. So I guess when you're Euler, you just create a new branch of math. And that's what we know today as graph theory. So what he was able to do was think about this picture in a little bit more simple detail, where he removed some of the trivial things, and he thought of the bridges as edges. Okay, so we have 7 edges here, and these edges connect certain, let's call these vertices. That'll make more sense later. But the black space are vertices, and in between these we have edges connecting them. And what he noticed was it was impossible to do the question, to traverse everything only once. And he found this out by proving, certain edges and vertices have degrees, and that you would need a even number of edges in this case to do what was told. So you might be thinking, well, how does this, town or map really look like a graph? This doesn't really look like a graph at all. So how do we represent a graph in modern mathematics? So here is a better representation of a graph. We'll call this graph G. And G has a set of vertices and a set of edges. The vertices here are A, B, C, and D. And the edges are the lines between the vertices. So we have an edge between A and C, B and C, C and D, etc. And every vertex has a certain degree. The degree is just how many edges are connected to that vertex. So the vertices set doesn't really get too complex. It just lists the vertices. But the edge set, we can kind of get a little, fancy with it. And there's two main ways to describe the edges. We have an adjacency list and an adjacency matrix. So the adjacency list takes an arbitrary vertex, so vertex 1, and it describes where I can go from this vertex, the neighbors that it has. So from 1, I can go to 2. Okay, so that is shown here. From 1, I can go to 2. If we go to 5, from 5, I can go to 2, I can go to 4, or I can go to 6. So if I look at 5, yeah, I can go to 2, I can go to 4, or I can go to 6. So that is perfectly shown there. Adjacency matrix is a little bit, not as easy to see, but it's the same idea. If we start at the vertex 1, which is right here, and we say, hey, can I go to vertex 2? So then I go over to column 2, and I see that there's a 1 here, and that means that that's true, so I can traverse that. You might be thinking, well, this graph has like arrows and stuff. So it's a little bit different than the graph G that we looked at here. And you're right. So there are actually different types of graphs. So here we have a directed graph in which the edges are directed and you can only travel in the direction that the arrow is pointing. So from 0, we can only go to 1. And from 1, we can either go to 4 or we can go to 2, etc. Whereas in an undirected graph, you can traverse edges in any fashion. So from A, I can go to A to B, A to D, D to B, vice versa. And in some instances of graphs, we have weights associated with the path. So there's kind of like a cost when you're traveling. If I went from 0 to 1, that would cost me 4. So if I wanted to get from vertice 0 to 1, and the minimum cost, I would go from 0 to 1 using the cost of 4 instead of going this way, which would cost like 19, so it's a lot more. Graph traversals. So I can traverse a graph using breadth first search or depth first search. There's other methods, but these are the most common. In breadth first search, I must visit all the adjacent nodes before exploring like the next depth, essentially. So if I was breadth first searching this graph here, I would start at A, and I would go to B, and then I would go to D. So I would discover these nodes before I moved on to the next ones, which is C and E. In depth first search, when you explore or when you discover a new node, you must explore it in totality before moving to a new one. So if I'm at A and I discover B, I must keep exploring until there is nothing else to explore. So then I would go to C, and then E, and then D. And then from D, I would try and go to B, but that's already been discovered. I'd go back. A's been discovered, go back. Everything from E's been explored, go back. Keep going back until I would return from the starting point and realize I've traversed the whole graph. Okay, so we'll look at what this actually kind of looks like. So here on the left, we have depth first search. On the right, we have breadth first search. And you notice that as the animation progresses, Depth first search, we go down the tree all the way till we can't explore anymore, and then we go back up and go down again. Whereas in breadth first search, we span out equally and keep going. The neighbors are discovered on the same level. We don't move to the next level until we explore the current level. And applications of graph theory are all over the place. If you've ever used navigation, which I'm sure we all have, you've used a form of graph theory, pathfinding, from one destination to another. Every computer network, whether it's local or the entire internet, can be represented in some type of graph, or a social network. You know, if you think about who you're friends with and who your friends of friends are, friends of friends of friends, that can all be represented in some form of a graph. So thank you. I hope you learned something. Here's some of the sources I used. And if you would like some more information about graph theory, feel free to email me. I have some great videos that explain it a lot better than I can. So have a great day.